Okay, YouTube, in this video we're going to introduce what we referred to as the unit circle in trig and math, but also go very much into detail of what it is and how it is useful before moving on to using it in practice. Okay, so we're just going to start with this right off the bat. It says, so we're going to start our investigation by considering a circle having the equation x squared plus y squared equals 1. And one thing I want to point out here is this. When we talk about the equation of a circle, we often say that it's x squared plus y squared equals r squared, where r is the radius. Okay, and so one thing I want to consider in this is that we have r squared would be this 1 right here. And so one thing I suppose to point out would be this. When we say 1 squared, or sorry, r squared is equal to 1, well then we could determine that r equals 1. So when we talk about the unit circle, it gets its name because its radius is 1 unit in length. Okay, so this is just some circle that is centered at the origin that has a radius of 1. You can see that here in the xy coordinate plane that I've graphed this here. So centered at 0, 0 at the origin. So for example, the point 1, 0 would indicate that our radius here is actually indeed equal to 1. Now, what this does is it opens up doors for us when evaluating, say, trig functions, because here's what I know now. Suppose we have the terminal side of an angle theta in standard position, some point x, y, okay? So it's the same circle you see up here. I'm just graphing some angle in standard position, which we know an angle in standard position just means that its initial side, remember the initial side is where it starts, is on the positive x-axis and its terminal side is where it stops. But we've known for a while now that if we had some point xy on the terminal side, then we could describe this as, say, some right triangle situation here, where we have y is the dimension of my triangle here, x is the dimension of my triangle here, and this thing right here we've been calling r. It's just that in this case, this is very profound, our r value is 1. So the thing that really we want to kind of make a connection on first before we move into anything else is this. If we were to use the definition of, say, sine, cosine, and tangent, that is, prior to this we say, well, the sine of some angle in standard position would be, say, opposite over hypotenuse, or y over r. I'm going to write that down here. We say sine of theta is equal to the y value of our point over this distance from here back to the origin. What I want to point out here is this. In this particular instance, if you're talking about not just some angle in standard position with the point on the terminal side, but some angle in standard position with the point on the terminal side and it intersects the unit circle, then we say that the radius is explicitly 1. So what we end up determining is basically this. We say, well, instead of y over r, if you're on the unit circle, you're saying it's y over a radius of 1, which is profound because what this means is that the y value of this point right here is literally telling us, we say x and y, it's literally telling us the sine value of this angle just by looking at the y value. And likewise, we could say, well, cosine. The definition of cosine would be this angle here adjacent over hypotenuse, or x over r. So we can say x over r. This is our definition here. But we say now the radius is 1 if you're on the unit circle. So since I'm on the unit circle, we say, well, then the cosine value must be literally equal to the x value. So this over here we could say is the cosine value. So basically, before going any further into this, the conclusion we can draw is that if you are on the unit circle, given some angle in standard position, and it has this point xy on the terminal side, but that's also on the unit circle, it means that every point on the outside of the unit circle is telling us the cosine and the sine value of that angle, which is pretty cool. Furthermore, I suppose before we move forward is this, what if I wanted to know the tangent of the angle? Well, we also know that the tangent is the sine over the cosine using our ratio identity, which in this instance we're saying must be this y value of my point over the x value of this point. So what we're going to do is we're going to spend some time now developing this entire unit circle over here. So this is kind of lengthy. I'm going to try to go quickly here, but we are going to fill out the most common points on the unit circle, okay? Starting with some pretty stinking simple ones right off the bat. So when we say the unit circle, first of all, let's go ahead and write this up in the corner. We are filling out a list of points here that are telling us the cosine of the angle and the sine of the angle. Every point on the outside of this unit circle literally tells us, say, the cosine and the sine of that particular angle, which is a cool thing. We're going to start by labeling some very simple points. Since we know that this is a unit circle, then that means that this point right here must be the point 1, 0 in the xy coordinate plane, because we went 1 to the right of 0, 0, and we've gone up and down none. Furthermore, we could say that this is 0, 1. We could say that this is -1, 0, and we also know that this is 0, -1. Okay, before I go any further, what this basically means is when you talk about, say, a 0-degree angle, or we could say 0 radian angle, we could say, well, if somebody asks me what is the sine of, say, 0 degrees or 0 radians, I could just go over here and look at the circle and say, well, then it would have to be this y value right here. It's just 0. So I could just refer to this circle right here. I could say, furthermore, what if I wanted the cosine of 0 degrees? Well, we could say it's just the x value at 0 degrees, and I say that's 1. And furthermore, even still, we'd say, well, then what is the tangent of 0? And we say, well, really what it is, it's the sine over the cosine of this, okay? So if we were to take the y value here over the x value, the sine value divided by the cosine value, we'd get 0 over 1, which is just 0. Okay, so this works for all of these angles here. Our job now is to not just know these quadrantal angles and their values, but also these angles in between. So what I want to start with is this. I want to fill these angles out. We say this is a 30, this is a 45, and this is a 60 here. Okay, I am not going to go ahead and fill out any of these other quadrants yet. I just want to look at the first quadrant. We're also going to label these angles in radians. So we say a 30-degree angle. Well, we know that 180 degrees, which is this guy over here, 180 degrees, that's the same as pi radians. So 30 degrees must be a sixth of pi, or pi sixth radians. 45 degrees, I can get 1, 2, 3, 4 of those into pi. So we say that's a fourth of pi. A fourth of pi. And then we say 60 degrees, that goes into 183 times. So this must be a third of pi. And of course we know that, say this angle here, this 90-degree angle, is half of pi. It's half of 180. So we said we were just going to deal with this first quadrant up here. That's what I want to look at first. Now, if we were to consider what are the x and y values of this first point right here, what I want to consider really is this. I'm going to sketch in this right triangle right here as if we had one, and say that the thing I want to point out here is that the r value is 1. Okay, so I'm looking at this 30, 60, 90 triangle here where the r value is 1. So now that triangle I sketched in, I'm kind of going to come over here and work with it off on the side, but we are already very, very, very familiar with 30, 60, 90 triangle. So if this is 30, this is 60, and what we're saying is, in this case, this is 1. So could we work backwards to find, say, the x and y value of this? Well, what I know is when you deal with a 30, 60, 90 or any special right triangle, you always look at the short side first, and I suppose we could just say it's equal to some length a. But what I know is if this is a, then the hypotenuse is twice as long as a, and this side down here is a root 3. So if I just knew what a was, then I suppose I could work backwards and figure out what x and y were here. I could fill that in. What we do know, though, is this. We say, well, if 1 is my hypotenuse and that's equal to 2a, if we were to divide both sides of this by 2. And it's not important that you remember how I'm getting these, just that I get them here. We say that a would be a half. And so what this means is that our y value here is actually equal to a half. Okay, we say, well, then what would my x value be equal to? Well, x is equal to a times the square root of 3, where we know what a equals. We've just determined that a is a half. So I get a half times the square root of 3, which is really a square root of 3 over 1. So we get root 3 over 2, essentially. So we say the x value here, the x value on this particular angle here would be square root of 3 over 2. Okay. So now one thing I kind of want to mention before we move forward is this. If I were to be considering now the 60-degree angle, the thing is I don't have to go through all this math again. I hope you can see that there's a definite relationship between these two triangles here. It's really the same triangle, kind of listed a different way. You see the short side here would correspond to this x value on this point here. And we say that this long leg here that was representing our x value before here would represent this long leg here, which is actually the y value up here. So what we can say is then, if this is root 3 over 2 and this is a half, then this point here must be, oops, let me switch colors here. This is a half and this is root 3 over 2. Okay, so this last triangle I want to pick on here is what if we had, like I say, a 45-degree angle here? And I just kind of want to really point this one out. This is our other special right triangle, but we'd say this and this would have to be the same thing. So whatever we get for x and y here, they have to be the same thing, but recall that the radius is 1. We're on the unit circle. So again, you don't have to recall how I'm getting this, but what if I were to draw our 45, 45, 90 off on the right here, in which we know that this is our 45, this is also 45 degrees, that our y value and our x value here are congruent, they would have to be the same thing, but furthermore that the radius is 1. So again, we would just work this out. We'd say, well, looking at the short side, we'll just call the short side some length. And again, since it's isosceles, this is also, say, the short side here. But we say in a 45, 45, 90, the hypotenuse is always equal to the short side, which we're calling a times the square root of 2. So again, we could say, well, hey, if 1 is equal to a root 2, then we could divide both sides of this by the square root of 2. And what I determine here is this. Well, then I get a equals 1 over the square root of 2, which is actually, when we rationalize this, equal to the square root of 2 over 2, square root of 2 over 2. So what that means is that our x value and our y value at this 45-degree angle are square root of 2 over 2 and square root of 2 over 2. So now, before I deviate into any of these other quadrants, let's talk about why this is beneficial. Again, recall from what we had just mentioned that every point on the outside of this unit circle is telling us both the cosine and the sine of the angle that we're looking at here. So, for instance, if I were to say, please and thank you, would you go find the cosine of 45 degrees? Well, if I know my unit circle, I could say, well, here's 45 degrees right here. I know that the cosine values correspond to the x values, so we could say, really then, the cosine of 45 degrees is just root 2 over 2, just by looking at this unit circle right here, okay? So what are some things I want to kind of mention about this unit circle? Well, the first thing I want to mention is this. You notice that I put these kind of angles down here. We are going to actually label all of our angles now, so let's go ahead and do that. But we say, what degree would this be here? Well, what I know is this. This leftover right here, if I were to consider this as 60 degrees, but what would be the actual angle right here in standard position? Well, if that's 60, then this must be 120 degrees. Okay, so we say this is 120 degrees, or we could say it must have been 90 plus another 30. So this is 120. This right here would be 90 plus another 45. So this is 135 degrees. 135 degrees. And then this one right here would be 90 plus 60, which would get us 150 degrees right here. You could also look at 150 as being 30 degrees shy of 180. This one, 135, is 45 degrees shy of 180, and 120 really is 60 degrees shy of 180. So we're still picking on like 30, 45, and 60 here, okay? Going down here, we'd say, well, this would be 30 past 180, so this is a 210. This one here would be 45 past 180, so this is 225. And this one here would be 60 past 180, which gives us a 240 degree angle. And then coming over here, working backwards, we could say, well, full rotation would be 360. So this angle right here would really be 30 degrees shy of 360. Okay, so 30 degrees shy of 360 would mean that this angle is like a 330. This angle right here is 45 degrees shy of a full rotation. So we would say that this would be a 315 degree angle. And then this one right here, I don't know, it's like 30 degrees past 270, or it's 60 degrees shy of 360, but we say this is a 300 degree angle. Okay, so now going back and putting in our radian measurement here, I do want to make sure that I can put those in, but we say pi 6 is 30 degrees, so pi 6 would be 30, 60 would be 2 pi 6. Recall that 2 pi 6 is the same thing as pi thirds, so that's why we write pi thirds and we don't write 2 pi 6. But we could count around, we say, okay, well then this 90 degree angle would be 3 pi 6, or that's the same thing as pi halves. But when we get over to this 120 here, we say it's 4 pi 6 radians, or 2 pi thirds, okay? We say 135, we would say that'd be 1, 2, 3 of these pi fourths things, okay? And then we say, well, this 150 right here would be like 1, 2, 3, 4, 5 30 degree angles, so this would be 5 pi 6 here, okay? So for the sake of time, I'm going to keep filling these in. We say, well, 6 pi 6 is 180. This is 7 pi 6 here. 7 pi 6. Another 30 would be 8 pi 6, which is really just 4 pi thirds, or 4 60 degree angles. This would be 9 pi 6 down here at 270 degrees. So 9 pi 6, that simplifies out to 3 pi halves, or 3 90s. Okay, this would be 9 pi 6. This is 10 pi 6, which is the same thing. 10 pi, let me write this out. 10 pi 6 would be the same thing as 5 pi thirds, but that's reasonable because this angle down here is 5 of these 60 degree angles, so 5 of these pi thirds things, 5 pi thirds. And then we say this right here would be 11 pi 6, 11 pi 6, and then 12 pi 6 would bring us back around to 360, or we could say just 2 pi rotation. So now the only ones we didn't really fill in here were our 45s. This is 1 pi fourth, 2 pi fourths, 3 pi fourths. This would be 4 pi fourths. This one here is 5 of these 45-degree angles, 5 pi fourths, 6 pi fourths, but that's the same as 3 pi halves, and this is 7 pi fourths here. Okay, so we get all our radian and degree measurements in here. What we want to do is go ahead and finish out what this circle is, okay, by filling in these values up here, because we want to know them. We want to know which trig functions are equal to what at those given angles. So notice this. If I were to say, look at any angle that has, say, a reference angle of 60 degrees here. So that would be like this angle here has a 60-degree reference angle. If I were to drop this down here, you notice that these two triangles that we're looking at here, these two right triangles, they are congruent. And so what this means is when you look at their actual values that are up here, so for instance at 60 degrees I notice I get 1/2 and square root of 3 over 2. Well, then over here I'm still going to get 1/2 and square root of 3 over 2. The only difference is that when you're in the second quadrant we're dealing with negative x values. Okay, so likewise we say that this one's going to be root 2 over 2, root 2 over 2, but our x values are negative. And this one here is going to be square root of 3 over 2, 1/2, but negative root 3 over 2, and this would be 1/2. Okay. So we'd say, moving on, why don't we take a look at this down here? Well, this would be identical, to say anything that has a 30-degree reference angle here. So we could just really look at this value right here and fill these in for anything that has a 30-degree reference angle. But this one here would have to be root 3 over 2, comma 1/2, just by looking at this right here. Okay. Also, this one over here would have to be root 3 over 2, comma 1/2. The only differences are down here we have a negative root 3 over 2 and a negative 1/2, and over here we have a positive root 3 over 2 and a negative 1/2. Okay, so signs are the only things that are different. So filling in the rest of these, we say root 2 over 2, root 2 over 2. This one over here, root 2 over 2, root 2 over 2. We know this because we look at anything with a reference angle of 45 degrees is going to give us an x and y terminal point of root 2 over 2. It's just we need to adjust the sign. So negative x, negative y, positive x, negative y. And then we'll go ahead and fill in these right here. We say they would have to be the same as these right here. So we'd get 1/2. Let me get those out of the way. That was ugly. We get 1/2 root 3 over 2, but in this case both negative. And then we'd say over here we'd get 1/2 and root 3 over 2, except for our y value would be negative. Okay, so now that we've got this entire unit circle filled out, you notice on the outside it says positive and negative. And all I want to write is kind of this A, S, T, C. And so we could fill this out, but basically it says, well, which ones are positive up in the first quadrant? Well, what I want you to know is that you're going to get a positive cosine and a positive sine because all of our x and y values are positive. And also this, if I were to do tangent, say sine divided by cosine, I would get positive values as well. So tangent's also positive. This S here would regard sine. It says the only things that are going to be positive here are your y values. And we also know that on the unit circle, the y values are the sine values of those angles. So those would be positive. Everything else is going to be negative. Now, I include cosecant as being positive because cosecant is the reciprocal of sine, and so if something's positive, its reciprocal is positive. But let's go ahead and put this into practice. Now that I've got this unit circle on me, I can start to ask questions like this. What is the sine of, say, 120 degrees? And what this means is I could just go over here and look at 120 degrees right here, or 2 pi thirds radians, and say, well, the sine would be equal to the y value, so it's just root 3 over 2, and I'm done. That was very, very quick. Likewise, what if I said, well, hey, go find me the tangent of, say, a 225 degree angle. Now, all I have to do is recognize two things. First of all, I'd have to go find 225 degrees, which is this right here. But I'd say I want the tangent. Now recall, tangent is sine divided by cosine. So in this case, I'd have to take the y value divided by the x value. I get negative root 2 over 2 divided by negative root 2 over 2, which anything divided by itself just gives us 1. So I'd say, well, then the tangent value right here is 1. Okay. Furthermore, let's do one more. We say cosine of, say, I don't know, a negative 30 degree angle. Now remember, 30 degrees negative doesn't show up on my unit circle here because we only talk about angles between 0 and 360. But if I were to go negative 30 degrees, that would be an angle here, negative 30 degrees. And I want to go find the cosine of this. I suppose I could just go look at this x value right here because it represents the cosine at that angle. So I could say, well, it's just root 3 over 2. But the only thing you need to know on this entire unit circle really is this first quadrant. as well as your 4 quadrantal angles, because this is just going to tell us how the other 4 quadrants behave, because you'll notice that all these points were identical in each of the 4 quadrants given some reference angle. Okay, so that is the entire unit circle. Don't lose this because we're going to use it